Okay, well, we set this up. I'm going to introduce our second speaker of the session, Romina Molina. She is a researcher and engineer specializing in applied AI and embedded systems. Her work focuses on machine learning model compression and deployment of FPGA or SoC platforms with applications in nuclear science, environmental monitoring, and others. Following her postdoctoral work at ICTP, she founded KalEdge, an AI consultancy delivering training and development services internationally. And welcome, Romina. I guess today you'll be telling us about the framework your company built, KalEdge Lite. Go ahead.
Thanks a lot. Thank you, everybody, for being here. I'm going to introduce today KalEdge. This is a sort of platform, dashboard, web-based, in order to cover the complete pipeline from machine learning model training following compression. And after that, guiding a little bit to the machine learning model implemented on the FPGA part using hls4ml as backend. Since my experience in this topic during my PhD, then postdoc and research, what I've been noticed that we have several challenges related with all these technologies available nowadays. So mainly we have the FPGA itself. Then the tools related with the FPGA. In the world of FPGA, we have several platforms ranking for Sync, UltraScale Plus, and also nowadays we see Versal AI. So that's one thing. The other thing is, OK, if I want to train the model, what are the concepts related with the models? And then if I want to compress the model in order to have it running completed on the FPGA part, what compression techniques should I use? How I should combine them? And then if we move towards, OK, I have the software, how we're going to deploy it into the FPGA part. So I will need a sort of bridge, for example, hls4ml, BTC AI, and FIN. So we start to add a lot of things on top, right? So we have a learning curve, a little bit challenge at the end of the day, right? So we don't have, we have a lot of algorithms and tools nowadays. But what I've been noticing is that we are missing a sort of integration, right? So in this case, we need to coordinate model design, compression. In my case, I'm working mainly with high-level synthesis, and also everything that is related with vendor tool chains. Then another thing is, OK, if I want to compress a model in a way that it will run on the FPGA part, and how I will know the resource utilization and latency without going into the synthesis process, right? So in that sense, we have an iteration cost that we need to be aware of that, at least at the beginning until we start to develop a sort of intuition. So the workflow and this dashboard, what it does is comprise everything, right? From the upload the model. There is an agent there that will recommend some sort of preprocessing to apply to the data set. After that, we are going to design the architecture. It supports nowadays multi-layer perceptron, convolutional neural networks, 1 dimension, 2 dimensions. There is also an AI architect based mainly on natural language in order to define the architecture. For example, if I want to implement a 2-layer multi-layer perceptron, the user can define it in that way. Then we will need to train a model, a baseline one, that then is going to be compressed and optimized using several compression techniques. Then we can evaluate and compare the different models. And after that, we have the option to, using an estimate surrogate model, to estimate an early stage of the design, the latency and the resource utilization. And if we say, OK, this will fit more or less in the FPGA part, we will convert it using hls4ml in this case. And then there is also a sort of secure tunneling where the user will have has installed the vendor tool chains in their own station. So the application will launch the BT's HLS, will launch also Vivado. So it will create a sort of base framework to assess the machine learning model in the FPGA. This application was tested with more or less 70 participants across different FPGA trainings in Argentina, Italy, Spain, and also online. And this is the platform. As you can see, it's a tab-based. So we have, following one tab after another, you can move forward through the complete process. And then regarding compression techniques, it supports several, like pruning, right, to remove redundant neurons and connections, kernels. Quantization, mainly quantization our training, quantization our pruning. Then we have also knowledge distillation, that the main idea with knowledge distillation is to shrink the model. We have also low-run factorization. And then also, this part of the application allows you to combine different techniques, right? Because we can have, OK, only quantization, only pruning, only distillation, and then we combine. At least for now, and regarding my experience in different applications, such as nuclear instrumentation, precision agriculture, and environmental monitoring, I will notice that when we combine the techniques is when we get the best model to be implemented on the FPGA side. This is the surrogate model that is mainly based in hls4ml in the sense that when we model, when we want to estimate the resource and latency for a given code, the modeling is tied to the implementation of that hardware. We can say it in this way. So in this case, after several syntheses of different models, mainly multilayer perceptron, three modes were identified, three regimens: compute bound, reuse bound, and latency dominated, that are mainly correlated with a reuse factor that hls4ml has. The reuse factor is mainly related with the amount of multiplier that I will use for the different operations. If the reuse factor is 1, I will have the maximum parallelism. If the reuse factor starts to increase, I will start to have resource sharing. So the analytical estimations take into account the resource, the model size, the precision, and also the parallelism, and how the pipeline is fed at the end of the day during the several layers. This is, I'm not going to dive into the details for the mathematical part, but the main idea here is that you can observe from the different models how the reuse factor that is R is in all the computations, and also how the M that stands for the different max operations are also involved in this process. Then we have several constants that were obtained after fitting the model using linear and nonlinear regression techniques. So the main idea with this estimator is to have a hint at the beginning before going into the FPGA. The main goal of this is not to replace HLS, right? We will need HLS in order to generate the IP core list using hls4ml. What we can observe from this point of view is we are going to speed up the design space exploration a little bit. It's not the same to run a synthesis for a defined model that it may take 40 minutes, 20 minutes. Instead, the model will run in milliseconds. So we have there a sort of a speed up regarding the design space exploration with this type of modeling. And regarding the accuracy, as you can observe here, all of the values regarding with the mean absolute percentage error are below 10%. And that is quite acceptable because what we want to have is that first hint in order to see how we move forward with our application, right? Usually, people ask, OK, if I have a model of 6,000 parameters, it will fit into the FPGA or not? If I have 8,000 parameters? So those are the questions that start at the beginning. So the main idea with this platform is to lower the barrier for the entry point in this type of workflow and technologies. These are the results in comparison regarding HLS and estimation for the different models. The application was a gamma neutron discrimination in the context of nuclear instrumentation, and then also MNIST dataset tested with multi-layer perceptron also. And here we have both sync and UltraScale plus. The main idea with this is to see what happened with the surrogate model with these two type of families. The model is supporting UltraScale plus after fine-tuning the different equations and values. Then it's also, for now, adapted for Vivado HLS 2024. So maybe if we move towards Vivado 2022, maybe some of these equations need to be adjusted a little bit based on the overhead that we can have between the different implementation of the operations performed by the vendor. And for now, what is working is, OK, multi-layer perceptron based, not based, a surrogate model applied mainly for multi-layer perceptron in two families. Then we have 3 agents for this platform. 1 agent for the data set in order to propose some pre-processing, another agent for the architecture itself, and another one is an AI advisor. The main core for the AI advisor is to give you some hints regarding the techniques that you need to apply, taking into account your application and the FPGA part. And CNN, OK, is planned to be extended to CNN architectures also. Then the thing related with how the sparsity impacts in the different hardware. And for now, there is also a simple implementation of a spiking neural network integrated in the platform. So mainly with HLS, the main idea is in the future is also to integrate the training of the spiking neural network architectures. And then regarding brief conclusions about that, the main idea with this is to have a new unified end-to-end workflow that will go from training models till FPGA deployment. Then we have this regimen-aware analytical surrogate model in order to speed up the design space exploration, to have several hints regarding the latency and resource utilization with 10% lower MAPE value. The dashboard was tested and validated with more or less 70 participants. And the future directions were more or less what I showed you before. The thing here, what I want to show you is this is KalEdge. This is the application. Here we can, for example, load the data set. It supports MNIST, for example, CIFAR, and we can also upload the data set. Here we have the input mode. In this case, we can train with the multi-layer perceptron in a flattened manner, so it's going to be in 1D. Here we have the architect. Here we have the definition of the different architectures. I will load a basic multi-layer perceptron architecture, for example. I will verify and summarize everything, the number of parameters that I have. Then I have the training tab. Here we can train the baseline. And here we have also the different compression techniques. We can, for example, move here till 8 in order to make it a little bit faster. We also have a scaffold cross-validation that is related mainly when we have a small data set. And we will see that each tab has also its own metrics associated with the different results. Here we have the accuracy, precision, recall, F1 macro parameters, model size, and the different curves. Here we have the AI advisors, taking into account the tasks that we want to do, the hardware platform, the compression strategies, precision, and so on. The pipeline is devoted to have to combine different compression techniques, as we can observe here. And here we have a tab of report, which each model will have its own report associated. Here we have, for example, the confusion matrix after the training, the weight distribution that we have. And here we have, for example, the estimator. And this is the fusion with hls4ml, where the main configurations are present in this dashboard. We can convert it here. And the important thing here is, OK, we will convert the model using hls4ml, but we need to also check how the model behaves. So at the end of the day, we have also a C++ simulation. And the tool also supports the generation of the DMA wrappers in an automatical manner, taking into account the input and the output of the different layers. Here is the result of the HLS simulation. And then the main idea is to download the project in the notebook, and then in the part of the firmware, we will have to establish the connection with the tunnel in order to launch the different the synthesis processing with HLS and the Vivado. So that was a brief overview, and thank you so much.
Thanks a lot, Romina. Questions for her? Here, go ahead, Johnson. Grab a microphone. Can you grab a microphone?
Thank you for the talk. Regarding circuit model, it seems that all of the activations and weights are 16 or 8 bits.
Yes, you can fine-tune those. You can use 4 bits, 2 bits. You will need to train, for example, the model if you want to go for a quantized version using QKeras. And then in hls4ml, you will adapt.
I'm asking about circuit model.
Sorry?
About your circuit model, because there's no mention of the bit widths. You only count about the MAC operations.
But you are talking about the surrogate model.
The surrogate
yes,
model.
For now, it's taking into account 8 bits and 16 bits. That is, yes, the limitation.
And everything is in resource strategy?
Sorry?
Everything is in hls4ml resource strategy or latency strategy?
I don't.
Are you using hls4ml resource or latency strategy?
Both. With regarding hls4ml. Because in that part,
the surrogate model will be different under these two assumptions.
I don't understand.
And is the surrogate model you are mentioning in the presentation targeting the resource or latency strategy?
The modeling is taking into account the hls4ml implementation. If you design the resource modeling, the C++ code will have one behavior. If you target the latency, we have another behavior.
I'm a developer of
yes.
HL4ML.
So at the end of the day, the model is considering both strategies because you analyze how the code behaves.
OK, so the strategy is
one and another
encoded as a parameter in the surrogate model.
Sorry?
The strategy is encoded as a parameter in the surrogate model.
Yes. There are some sort of, not everything is there in the slide, but there are some sort of variables inside the surrogate model that take into account that part of the hls4ml implementation. Because the main idea with the surrogate is that, to understand what you have in the C code, what are the options that you have, and then, based on that, perform the estimation after running the synthesis.
OK,
yes.
Since there's no RAM usage, it seems that everything is in I/O parallel. Is that correct? Are you using I/O parallel?
I/O parallel? No. Why I/O parallel? Sorry, in the HLS.
In hls4ml configuration.
Yes, HLS I/O parallel and I/O stream. You have mainly I/O parallel, I/O stream. Then you have the number of bits.
Yes. Is that accounted in the circuit model?
Yes.
And because there are many parameters, like 20 in
yes,
the circuit model,
but
and how many?
I'm not counting all of the parameters, mainly the ones that are I'm working on, at least for now, because the idea with this is to scale a little bit towards adding architecture. For example, your stream will be mainly related with convolutional neural network, for example, right? Convolutional neural networks are not supported yet.
OK.
So at the end of the day, it's towards to have an efficient model.
Thank you.
Okay, any other questions for Romina? Do you have your mic?
In your surrogate algorithm that you try to approximate the LUT latency or DSP model before, for example, synthesized by Whiteys, you know that I remember you used the reuse factor in your latency formula that you show us. You know that in the Whiteys, when we increase the reuse factor, it's increased the time, but we expect
Yes.
that decrease our LUT. But unfortunately, we did not saw that because it's increased our control part.
Yes,
How do you?
that happens
Yes, yes.
also.
How do you injected this part in your formula that it helps you to, for example, approximate your latency more accurate before?
Yes, you have here 3 things in the latency, right?
Yes.
The one is related with the reuse factor. That is, you have A and B that are constant, obtaining after running and synthesis, and also applying linear and nonlinear regression in that part in order to obtain those values. And then also you have the S out and S ref that is related with what happened with the pipeline between one layer and another, because there you have also latency, how the different pipeline is filled, right? And then you have also this small network correction factor, because what happening is that when you have small architectures, you will have one behavior. When you have bigger architectures, you will have another ones. Maybe the overhead is covered also by the first part, because reuse factors account for that. So maybe you will have, when you have reuse factor of 1, you will have most probably routing congestion also, because you will have everything running into parallel. The latency will be reduced. But if you have a small model, for example, the bringing up, we can say in that way, we will take more time than the computation itself of the architecture, right? That's why you have that relation in that part.
Okay.
But the constants are obtained through running several syntheses and analyzing all that.
Okay, let me check with each other. What is A in this formula A?
Those are values that are related with, after applying several synthesis processes for different architectures,
Okay.
we ended with this type of relation for using the reuse factor, right? It was an empirical
A is this
definition.
Or R is this? R is the reuse factor or A is the reuse factor?
The A and B are values, right? Are coefficient latencies that were obtained after running several synthesis processes and to see what happened with the different size of the model. So there are some sort of coefficient extrapolated from that point.
You save them in the library and
Yes.
then use it?
Everything is internal, yes, yes.
Okay, and what is the B? BB.
The B are also related with the thing, the minimum is also a parameter that is related with the minimum logic that you need to bring up the FPGA part in that part, right? Then you start to account for the matrix, for the MAC operations, and that you have the M and the alpha, right?
And R is reuse factor, yes?
And the reuse factor is always one way or another related with that at the end of the day. Yes, because you will see that for some sort of model, you will change the reuse factor, but mainly the loops will remain the same. You're not going to see any improvement in the results, for example, right?
But I'm trying to find the relation between this and control pass and logic pass. I couldn't
Yes,
find it.
and for that, we need to explore this a little bit
Okay.
deeper. Then I can show you if you want the coding.
yeah.
That's
Thank
not a
you
problem
so
at all.
Yeah, so we do need to move on, but thanks again, Romina.
Thank you.